this slide right here, we're going to be dealing with the special right triangles. So special right triangles are 45, 45, 90-degree triangles and 30, 60, 90-degree triangles. Now, when you guys have your ACT test in November, what is it, March or February or March, whenever the state pays for everyone to take the ACT test, a lot of the times on the ACT test, they will ask questions that deal with the special right triangles. You don't have to have them memorized to be able to do them on the ACT, because you can usually do things like Pythagorean theorem and other things to get the answers. But if you know what the special right triangles are and have them memorized and can use them, that just speeds up the process on the ACT test where it's multiple choice, because you can get your answer faster. Okay, so the special right triangles, and these were the ones when I derived the unit circle. These were the rules, the triangles I was using when I derived the unit circle in that video. Okay. So the way that those formulas, the special right triangles work, is if I have a 45, 45, 90-degree triangle, well, in geometry we learn if we have two angles in a triangle that are the same angle measurement, if they are congruent, then the sides across from those angles are also congruent. So if this length right here is x, then the length across from the other 45-degree angle is also x. So where I put one little marking on each side of that triangle, the ones that each have one marking means they're congruent. They're the same length. So this length right here I know is x. And then if I did Pythagorean theorem, anytime you have a right triangle and need to find a side length of a triangle, Pythagorean theorem lets you find the third side. So a squared plus b squared equals c squared, where a and b are the two sides that make up the 90-degree angle, and then the c is the side across from the 90-degree angle, which is the hypotenuse. So if I took my x and then squared it, and then did my other x and squared it, that's like doing a squared plus b squared, and set it equal to c squared. If I wanted to find out what c was, well, I would just do x squared plus x squared, so I have 2x squared equals c squared. And then I would do the square root of c squared to get the c by itself. So then I would have c equals, and then when I have two things under a root, as long as they're being times or divided, I can individually break it into two separate roots. So I can write that as root 2 times root x squared. And then the root x squared part cancels and just leaves me with the x. So the x is no longer in the root, so I can write that as x root 2. So now I know that hypotenuse, or that c, is x root 2. So if I know two legs of a right triangle, and they're a 45, 45 degrees, 90 triangle, then if I knew, like, say where this x is, if I knew that was 5, then this other leg would be 5, and then the hypotenuse would be 5 root 2. If I knew that this x was a 10, then this leg would be a 10, and then this hypotenuse would be a 10 root 2. So then on the ACT, if you know that, it's quicker to get the answer, because then you don't have to sit and do Pythagorean theorem to come up with it, where the test is timed. If they gave me the hypotenuse, let's say we knew the hypotenuse but not the leg. So if they told me, say the hypotenuse was 10, then I would say x root 2 equals 10, and then I would just solve for x. So I divide by root 2. So then x is 10 over root 2. But then they usually don't like roots on the bottom of the fraction, so then we'd rationalize by timesing by root 2. So it would be 10 root 2 over 2, which would be 5 root 2. So then I would know both of these legs would then be 5 root 2. So whichever part you know of a 45, 45 degree 90 triangle, you set that equal to either x or x root 2, and then you can solve and get whatever length you need. Okay, now the 30, 60, 90 triangles, that one actually comes from an equilateral triangle. So here, equilateral or equiangular. So an equiangular triangle means all the angles are the same angle measurement. So if I had a triangle where all the angles were the same, I know in a triangle all the angles add up to 180. So then if I divided that by 3, I get 60. So each angle in this triangle would be 60 degrees. So this right here would be 60, 60, and 60. And then again, from geometry, if angles in a triangle are congruent, the sides on the opposite sides of those triangles are also congruent. So then I would know that the side across from this 60 degrees, right there, would be congruent to this, which is here. So all three sides of that triangle are the same length. So then here they said that this length from the center over was x. So then the length all the way across would be x plus x. So this entire length is 2x. So each side of this triangle is really 2x. And then what they did is they then went, in one of the angles, they just went and cut it in half so that this angle right here is now 30 degrees, and they made a right triangle. So now just taking that right triangle portion, we know that this length is x, this length is 2x, this angle up here is 30 degrees, this angle is 60 degrees. So I actually know stuff about two sides of this triangle, and I'm just missing the third side. That's right, the leg. So if I called that, say, A, I could do Pythagorean theorem and figure out what A is. So Pythagorean theorem, again, A squared plus B squared equals C squared. So I take the two sides that form the 90-degree angle, square them and add them, and set it equal to the hypotenuse. That does not stay very well. Okay, so then I go A squared plus x squared, that doesn't need to be in parentheses, equals, and then I do need to put the 2x in parentheses and square it because I have to square all of that hypotenuse. So now if I wanted to solve for A, I would minus x squared to the other side of the equation. So I have A squared equals, now 2x quantity squared, I would square the 2 and square the x. So 2 squared is 4, so I get 4x squared, and then I minus off my x squared. So then I get 3x squared. So A squared equals 3x squared. And then I just do the square root of that. So I can break that into root 3 times root x squared. So then A ends up being the x squared and the squared cancel, and I just get x. So I get x root 3. So now I know that of this 30, 60, 90-degree triangle, x root 3 is the length across from the 60-degree angle. X is the length across from the 30-degree angle, and then the length across from the 90-degree angle is 2x. So then if they gave me something of a triangle and I knew it was a 30, 60, 90, and let's say they told me the length across from the 60-degree angle. So let's say they told me the angle across from the 60-degree angle, let's say that was, say, 5. Well, I would set 5 equal to x root 3. So if I wanted to solve for x, I would divide by root 3. So I would have x being 5 over root 3, but then we don't like roots on the denominator of a fraction, so I just times by root 3 and get 5 root 3 over 3. So now, since that's x, I now know the length across from the 30-degree angle because that one was labeled as just x. So then this one is now 5 root 3 over 3. And then if I wanted to know the length of the hypotenuse, it just says you do 2 times whatever your x is. Well, so if I times this 5 root 3 over 3 by 2, I would get 10 root 3 over 3. So then I now know all the sides of that triangle. So if they had told me the hypotenuse, instead of, say, this length across from 60 degrees, if they told me the hypotenuse was, say, 5, then I would say 2x equals 5, divide by 2, and then I would know my x. Okay, so if you know these ratios, x, 2x, x root 3, you can always quickly find any of the side lengths on a 30, 60, 90-degree triangle. Okay. Again, you still could always just do it doing Pythagorean theorem, but on the ACT where it's timed, it comes in handy if you know these special right triangles. Okay, now this page, these are some identities that you need to, eventually you're going to get really familiar with if you don't know them yet. Did you guys see any of this at all last year in secondary math too? Yeah, okay. So these first ones, the reciprocal identities, sine of an angle is just 1 over cosecant of an angle. They're just reciprocals. So a lot of calculators don't have buttons that have cosecant, secant, and cotangent on them. Like my TI-84s, those of you that have TI-84s, 83s, you guys will have a sine, cosine, and a tangent button, but you won't have a cosecant, secant, and cotangent. Some calculators have all 6, okay? But if you have a calculator that only has these first 3 buttons, and you're given a problem in your book and it asks you about one of these other three, you just have to know reciprocals. So sine and cosecant are reciprocals of each other. That just means you flip the fraction. Cosine and secant are reciprocals of each other. You just flip the fraction. Tangent and cotangent are reciprocals. So the way that I remember which ones are reciprocals is the ones that tangent and cotangent, they both have the word tangent in it. So the ones that both have tangent in the name are reciprocals of each other. Now out of the sine and cosine, sine starts with an S. Its reciprocal can't start with the same letter. So its reciprocal starts with a C. Same thing with cosine. Cosine starts with a C. Its reciprocal can't start with the same letter, so it starts with an S. So if you ever try to do sine with a reciprocal with secant, no, you messed up because they both start with an S. Cosine can't go with cosecant because they both start with a C. They have to start with a different letter. So if it starts with a C, then it's an S. If it's an S, it's a C out of the sine and cosine, cosecant. And then sometimes people try to say sin instead of sine. The reason this is pronounced sine and not sin is it's really S. We just drop the E and use the first three letters. So it's sine, not sin. And that's actually cosine. We just use the first three letters. TAN is tangent. But again, we just use the first three letters. Cosecant. Cosecant. Secant. That one's the one that we do as CSC. And then secant, that's the one that we do as SEC. And then cotangent, that's the one that we do as COT. So we just use letters in them to name them. Okay, so now we have the quotient identities. So quotient means you're doing division. So tangent is the same as doing sine of an angle divided by cosine of an angle. And then since cotangent is the reciprocal of tangent, cotangent would just flip that fraction, and it's the same as doing cosine of an angle divided by sine of an angle. And then we have three Pythagorean identities. Let's use the most is this first one, sine squared theta plus cosine squared theta equals 1. I can actually see this one from the unit circle. On the unit circle, these ordered pairs are important because they give me the sine and cosines of various angle measurements. I wanted to know what sine of 30 degrees is. With these ordered pairs, it goes cosine, comma, sine. I just remember alphabetical order. C comes before S in the alphabet. So if I wanted to know what sine of 30 degrees is, I would expect it to be 1/2 because that's what the unit circle has right there. So if I type it into my calculator, sine of 30 degrees, make sure I'm in degrees and not radians. Sine of 30 degrees, it was 1/2. If I wanted to know what cosine of 30 degrees is, I would expect it to be √3/2. So if I typed in √3/2 to see what that decimal is, I get 0.86, which is what I got when I typed in cosine of 30 degrees. So all of those ordered pairs on the unit circle are telling you the answer to specific trig functions, specific angles. So the first number in the ordered pair is the cosine, the second number is the sine, and then to get the tangent, then we use those quotient identities, which said tangent is sine divided by cosine. So if I wanted to know tangent of 30 degrees, it should be the sine answer divided by the cosine answer, 1/2 divided by √3/2. Okay, that would be the same as tangent of 30 in the calculator. So this Pythagorean identity that says sine squared plus cosine squared equals 1. Well, from a unit circle, I know that the radius on a unit circle is always 1. And then if I took one of these ordered pairs, let's say the one at the 30 degrees. So at the 30 degrees, it says √3/2, comma 1/2. So that means the √3 would be the length from here to here because that's my x value. The 1/2 would be my y value. So if I did Pythagorean theorem, I would have √3/2 squared plus 1/2 squared equals 1 squared. So √3/2 squared, √3 squared would be 3, 2 squared would be 4, 1 squared would be 1, 2 squared would be 4, equals 1, and then 3 plus 1 is going to be 4, so I get 4 fourths equals 1, which is 1. But I know that this right here, that root 3 over 2, those ordered pairs, that was really cosine, and the second one was really sine. So I could have said cosine of 30 degrees plus sine squared of 30 degrees should equal 1. And I could try that in the calculator. Sine x, square it. Oops, I don't want to squared. Let me put in the 30 degrees, what angle measure I'm trying to do it at. And then if I did plus, and then cosine x, square it. Oops, I don't want to do x. I again want the degree angle measurement I'm trying to do it at, which is 30. Notice I got the answer of 1. So if any of these in the unit circle, any of these ordered pairs, if I added them together, I should always get an answer of 1. Because everywhere along the unit circle, that hypotenuse was 1. It's the Pythagorean theorem. So sine squared theta plus cosine squared theta equals 1. But those thetas have to be the same number. As long as they're the same numbers, they're both 60 degrees, both 45 degrees, it has to be at the same angle measurement. Okay, so another Pythagorean identity is 1 plus tangent squared theta equals secant squared theta, and then 1 plus cotangent squared theta equals cosecant squared theta. Okay. But again, the top one is the one that we use a lot. Okay, so now SOHCAHTOA. SOHCAHTOA can only be used if you have a right triangle. If it's not a 90-degree angle, you can't do SOHCAHTOA. So with SOHCAHTOA, the S stands for sine. Sine of an angle. I'm not going to write it as S-I-N-E. I'm just going to put the abbreviation S-I-N. So sine of an angle. The O, so we would say sine of an angle equals, the O stands for the opposite leg. The H stands for the hypotenuse. So the opposite leg divided by the hypotenuse. The ka part on SOHCAHTOA, the C stands for cosine. Cosine of the angle equals A stands for the adjacent leg. And the H stands for the hypotenuse. And then on the TOA, T stands for tangent. Tangent of the angle. The O is still the opposite leg. And the A is the adjacent leg. So if you have a right triangle, the legs are always the two sides that form the 90-degree angle. The hypotenuse is always the side across from the 90-degree angle, and it's always going to be the longest side in a triangle. So when it talks about adjacent and opposite legs, that labeling can change based on which angle they're having you look at. So we a lot of the times use theta to represent an unknown angle. So it's fine to use an X and a Y, but for some reason the mathematicians that be usually switch it to Greek letters when they deal with angle measurements. So you might see a theta, you might see a beta, okay, just representing unknown angle measurements. Okay, but it's just the same as if they used an X or a Y, okay? So basically, when you do SOHCAHTOA, you have to know what angle they're wanting you to figure out a ratio for. So they'll have one of the angles marked with like an X or a theta or something. So then when you figure out which side's considered the opposite leg, whatever angle you're looking at, you go on the opposite side of it. That's the one you're going to call the opposite. The adjacent leg is always the leg that's between the angle you're trying to figure stuff out about and the 90-degree angle. So the side that's formed between those two angles, we always call the adjacent leg. So if they wanted me, instead of doing the theta at that top corner, if they had the theta down here, then I would call this side over here the opposite leg. And then this one down here, because it's between the theta and the angle, I would call that one the adjacent. But the hypotenuse labeling never changes. The hypotenuse is always across from the 90-degree angle. Okay, so only the adjacent and the opposite that change based on the angle they're asking you about. Okay. So then this right here, SOHCAHTOA, lets you set up trig functions for like ratios using side lengths, and then you can use those ratios to actually figure out the angle measurement. So sine, I just memorize again, SOHCAHTOA, sine is opposite. So then if they ask me something about cosecant, I did these in red because the red one and red one, these ones are the ones that are reciprocals. Okay. So if sine is opposite over hypotenuse, then cosecant should be hypotenuse over opposite. Just flip the fraction. Cosine, on cosine is adjacent over hypotenuse. So adjacent over the hypotenuse, which means its reciprocal secant should be hypotenuse over adjacent. And then tangent was the TOA, opposite over adjacent. So O over A. So then cotangent should be the reciprocal, adjacent over opposite. Okay, and then here's a little note. If you're using a calculator, you have to be in the appropriate mode, degrees or radians. So anytime you hit a sine, cosine, or tangent button on your calculator, anytime you hit one of those three, the mode matters. So to check the mode, you hit the mode button, which is next to my second button. Right now, I'm in degrees. So if I wanted to do sine of 30 degrees, I could type it in right now. But if I wanted to know sine of root 2 over 2, sine of pi halves is radians, so I would have to change my mode into radians. So you just make sure you're in the mode based on whatever angle format yours is in. If it's in a degree angle, make sure your mode's degrees. If it's a radian angle, something with a pi in it, make sure you're in radians, because you do get different answers. So just to show you the difference, if I did say sine of 45 degrees, it tells me it's 0.7. In my calculator, 0.7 should be correct. Because if I looked on my unit circle at 45 degrees, root 2 over 2 should be what my answer should have been. So if I typed in root 2 divided by 2, it should be that 0.7 number, and it was. Now, if I'm in degrees and I tried to put the corresponding radian angle measurement, so 45 degrees corresponds to pi fourths. If I did sine of pi fourths, I'm not going to get 0.7. I get 0.013. But if I change my mode over into the appropriate mode of radians, now if I do sine of pi fourths, I should get the correct answer of the 0.7. And I do. Okay. So it doesn't matter if they give you angle measurements in degrees or radians, as long as your calculator is set to the appropriate mode, the answer should be the same. But if you're in the wrong mode, you will get the wrong answer. Okay, so this one says find the exact values of the 6 trig functions of the given angle. So we're given a right angle. It always has to be a right triangle. So in order to do the 6 trig functions, I need to know all 3 sides of that triangle. So if I know 2 sides of a right triangle, how can I get the third? Oh, let's go. Austin, how can I get the third side? Okay, so I could set up the sine, but what if I wanted to get this length right here? If I wanted to know what that length actually was? X squared. So that's perfect. So that's called Pythagorean theorem. So 5 squared, because that's the hypotenuse, equals, and I'm just going to call that side A. Square the other 2 sides, the 2 that make the 90-degree angle. Then we can get the third side. So 5 squared is going to give me 25. 3 squared is going to give me 9, plus A squared. So we're just minus 9 to both sides of the equation. So A squared equals 16. The square root of that is going to be 4. Now, normally when I've had you guys do square roots, I always said, when you're solving an equation and you put on the square root, put on a plus or minus sign. But in this case, I'm finding a side length of a triangle. Does it make sense to say my side length is negative 4 inches? Okay, so I'm not going to put the plus or minus on it. I'm just going to do the positive. Okay, so now that I know that, I can find all my trig functions. Now, Austin did mention that I could already know sine. He recognized that sine was opposite over hypotenuse, so he already said that should have been 3 over 5. So that one I could know without knowing all my sides, but once I wanted to know cosine or tangent, I had to know that third side. Okay, so using SOHCAHTOA, we just remember sine, the SO, again, stands for opposite over hypotenuse. So then what I sometimes do before I start working these out is I just label all my sides with an A, O, or an H, so I remember which one's which. The hypotenuse is always across from the 90-degree angle, so that's going to be where the 5 is. The opposite is across from the angle that you're looking at, so that 3 would be my opposite. The adjacent is always the one formed between the angle you're looking at and the 90 degrees, which is the 4. So I'm going to call it capital A for adjacent. So usually we'll just put those little letters next to it so I don't forget which one's which. So sine opposite over hypotenuse. 5. So then you just flip it. It'll be, okay, cosine, ca. The A stands for adjacent, the H stands for hypotenuse. So my adjacent, I already had it labeled as 4. The hypotenuse was a 5. And then secant, you just flip it, 5 over 4. And then tangent, TOA, opposite over adjacent. So 3, and then the adjacent was 4. So 3 over 4. And then TOA, we just flip it and get 4 over 3. Okay. Now the whole point of being able to do that is eventually we can then use that to come up with an angle measurement. If I wanted to know what the angle theta really was, then to get the sine off of the angle, we just do inverse operations. The inverse sine was like a -1. We talked about inverses before where we would do f -1. That's the notation for inverse. So if I wanted to know what that angle actually was, I would do inverse sine. So, and I want my answer in degrees. I prefer my angle measurements if I'm doing a triangle to be in degrees. So then if I went second and then hit the sine button and then typed in the 3/5, I now know that that angle measurement is 36.8 degrees. If I did the same thing with cosine, inverse cosine, and then typed in its ratio of 4/5, it should give me the same answer, 36.89 degrees. If I did inverse tangent of its ratio, 3/4, I still got the same answer. So we have you guys initially practice setting them all up, but then eventually we say, well, we don't need to set them all up. If we wanted to know the angle measurement, we only have to be able to come up with one of them. So then you look at your triangle and they usually give you 2 sides. And you say, okay, based on the 2 sides they gave me, could I set it up with sine, cosine, or tangent? And you just pick the one that you could use right away and then get your angle measurement. But initially we have you practice doing all of them. And then later we say, well, what's the angle measurement? And you just select the one you would need based on the information given. You could still come up with all of them, but they all still give the same answer. And then if my calculator had a cosecant, secant, cotangent button, I could do the inverse on those and get the same answers. Now, it does matter that you have the right trig ratio, because if I did inverse sine and accidentally wrote my ratio instead of 3/5 as 4/5, inverse sine of 4/5 is not going to give me the same answer. It gave me 53. Okay, so it is important that you have the right trig function set up with the right ratio. Okay, so it says use the given function values and the trigonometric identities to find the indicated trigonometric function. So I want to find stuff about sine, cosine, and tangent, and secant, and they gave me cosecant and a secant. What I'm going to do is I'm going to construct a right triangle. And I'm just going to call the angle down here theta. Okay, so they told me what cosecant is. And I always like fractions. So cosecant is like 3 over 1. So cosecant, if I looked up here, cosecant was in red. Cosecant is the reciprocal of my sine. So SOHCAHTOA, I know sine is opposite over hypotenuse. So cosecant should be hypotenuse over opposite. So this fraction should be hypotenuse opposite. So now my triangle, I now know that I need to label my hypotenuse as a length of 3, and I need to label the opposite side as 1. So the hypotenuse right here is going to be 3. The opposite side is going to be 1. So secant was the reciprocal of cosine. Before I do that, let me do this side right here. This would reduce to things. I'm just going to base it all off of the first one. So if I did the theorem to get my third side, just call it A. I would do 3 squared equals a squared plus 1 squared. So 3 squared is 9, so I get 9 equals a squared plus 1 minus the 1 over, and I get 8 equals a squared, and then I would do the square root of that. So the square root of 8, I know 8 is 4 times 2, and 4 is 2 times 2, so I can group 2's together and have 2 root 2. So I now know my length of a right here, that should be 2 root 2, and that's going to be my adjacent. So if I was looking at secant up here, secant is the reciprocal of cosine. Cosine using SOHCAHTOA is adjacent over hypotenuse, so secant should be hypotenuse over adjacent. Well, that doesn't look what I had here, but if I took my triangle that I had drawn and did the hypotenuse divided by the adjacent, did 3 over 2 root 2, and then got rid of the root on the denominator, then I have 3 root 2 over 2 times 2, which is 4, and it ends up matching up. Okay. It doesn't matter which of those you used, the first one or the second one, to construct your triangle, because they would both give you, in the end, equivalent triangles. Okay, so anyways, once I know all of these side lengths of that triangle, sine is that SOHCAH or the TOA part. Which one would we use to find sine? So, good. So, opposite, hypotenuse. So then we just look here, opposite I have labeled as 1, hypotenuse I have labeled as 3. So I can say I know that answer should be 1 over 3. Okay, cosine, that's going to be the adjacent over hypotenuse. My adjacent is labeled as a 2 root 2. My hypotenuse is labeled as a 3. Tangent, TOA. Opposite over adjacent. My opposite is labeled as a 1. My adjacent as a 2 root 2. So 1 over 2 root 2, but we don't like roots on the denominator. So then I multiply the numerator and denominator by root 2. Root 2 over 2 times 2, 4. So root 2 over 4. Okay, now this secant 90 degrees minus 0, that one is we have like even and odd identities. They might be listed in your textbook. Can I steal your textbook real quick? Usually textbooks give us this information on the front or back cover. So if you guys look in your textbook, and not the back cover, but if you flip one page over, this page is giving you a copy of the unit circle, those some of the reciprocal identities, the Pythagorean identity I mentioned, and then going down, there's one that says cofunction identities. Now, in the cofunction identities in your textbook, they all say like pi halves, halves minus theta. Well, pi halves is the same as 90 degrees. Okay, because in pi halves, pi halves radians is the same as 90 degrees. So then here, this one says secant of 90 degrees minus theta. So in your textbook, I'd find the one that says secant. So in your textbook, it says secant of pi halves minus u, your theta. It says that equals cosecant of the u. So then this angle right here, secant of 90 degrees, I would know that that's equivalent to cosecant of theta. So cosecant is the reciprocal of sine. So I can just take whatever my sine answer is and flip it. So my sine answer was 1 over 3, so cosecant should be 3 over 1. I knew the cosecant, that was one of the things they had given me to begin with. Okay, so in this one it says, given that sine of theta equals negative 84/5, and that the angle theta terminates in the third quadrant, the value of tangent theta. Okay. So basically, this gets to the stuff all students take calculus. All students take calculus. This lets you know which trig functions are supposed to be positive. In the first quadrant, if they asked you to do sine, cosine, tangent, secant, cosecant, cotangent of any angle that would land in the first quadrant, all of your trig functions are supposed to come out as positive numbers. So on your guys' unit circle that you just turned in where it had like that positive and negative, your positives should be sine, cosine, tangent, secant, cosecant, cotangent. None of them should be negative. All are positive. So all are positive. Now in the second quadrant, the S, students, the S stands for sine. Sine and its reciprocal. So in this quadrant, sine and its reciprocal, cosecant, are positive. The other four are negative. And if I looked on your unit circle, we can see there it goes cosine, comma, sine. We can see from our ordered pairs that the sine answers are all positive. The cosine ones are all negative. Okay, so in that second quadrant, sine and its reciprocal are positive. All the other four are negative. Okay, takes. All students take. The stands for tangent. Tangent and its reciprocal, cotangent, are positive. The other four are all negative. So sine and cosine and their reciprocal should be negative. And I can see in this third quadrant, cosine's negative, sine's negative. They both had negatives on there in those ordered pairs. And then C, calculus, that stands for cosine and its reciprocal, which is secant. Those are the ones that are positive. The other four are negative. So let's take calculus. Helps you remember which trig function should be positive and which one should be negative based on the quadrant that it lands in. Okay, so it says we're given that sine is in the third quadrant. So basically, if I drew a triangle in the third quadrant, when we draw these, we always start at the origin, go down into the quadrant they mentioned, and then you go straight up to the x-axis to make a 90-degree angle. The theta is always the angle formed at the origin. So where it tells me sine, if I did SOHCAHTOA, sine is the O part, I know opposite, sine is opposite over hypotenuse. So I would put, and I always put the negative with the top of the fraction. So my sine, that opposite, I would go opposite of my theta. So this side right here would be negative 84. The hypotenuse is across from the 90-degree angle. That would be 85. Now, even though I just drew a triangle where I had it like negative, I used a triangle to help me figure out the trig function, but in this quadrant, that is allowed to be negative because it's supposed to be a negative, comma, a positive to be in this quadrant. Okay, so movement-wise, it's fine to have a negative. Okay, so then if I wanted to find the third side, the adjacent side, which I don't know, I could just do Pythagorean theorem. A squared plus b squared equals c squared. Oops. So a squared plus negative 84 squared equals 85 squared. So I just go 85 squared, and then I would minus the negative 84 squared to the other side of the equation, and I get 169. So a squared is 169, and then if I do the square root of that, my a is 13. Now, quadrant-wise, I would have to move leftward to get over there, so I'm not going to call it a positive 13. I'm going to call it a negative 13 because to get into the third quadrant, it's negative, negative. Okay, to move that direction, my x value would have to be negative. So now I can answer whatever they asked me for. What did they ask me? And what is the value of tangent? Well, tangent, doing TOA, tangent is opposite over adjacent. So now my opposite side of the theta was the negative 84. My adjacent side was that negative 13. So my tangent of theta should be negative 84 over negative 13. Now, a negative over a negative is positive, so it's really 84 over 13. And all students take, the T on takes, the tangent was supposed to come out as positive, and notice it did come out as positive like I knew it was supposed to. Okay, so use trigonometric identities to transform one side of the equation into the other. Okay, so this is using some of these properties right here, or the properties in that back cover of your textbook that I pointed out. So it says tangent. So using quotient identities, tangent, I know, is the same as a sine over a cosine. Cotangent I know is the same as a cosine over a sine. So I could say, okay, tangent, I know that's the same as sine of theta over cosine theta. Times cotangent, I know is the same as cosine theta over sine theta. So now just doing normal math, cross-canceling, this sine theta could cross-cancel with that. Sine theta leaves me with a 1. I could cross-cancel that cosine with that. Cosine leaves me with a 1. So I get 1 times 1 over 1 times 1. So if they ask you to like show these using identity, they told me what the answer is supposed to be, and I have to show step by step how to get the answer. It's kind of like saying if I gave you an equation, I said the answer is 5, you'd have to show step by step how to get that answer of 5. This next one, I know the answer is supposed to be sine squared. I just have to show step by step how to get it. So what I could do is I could say, okay, I'm just going to FOIL these out. 1 times 1 is 1. 1 times negative cosine theta is negative cosine theta. Cosine theta times 1 is a positive cosine theta. And then cosine theta times cosine theta would be a negative cosine squared theta. So now my cosine theta and negative cosine theta would cancel, so I have 1 minus cosine squared theta. And I'm trying to show that that equals sine squared theta, so I go back to my trig identities. I'm trying to go and try to find one that has a cosine squared in it and a sine squared in it. So if I come back to here, under these Pythagorean identities, this does have a cosine squared and a sine squared in it. My problem said I wanted a 1 minus a cosine squared. So if I looked at this first Pythagorean identity, if I want a 1 minus a cosine squared, I could just say I'm going to minus cosine squared theta to both sides of the equation. So then those cosine squareds would cancel, so I have sine squared theta equals 1 minus cosine squared theta. That first Pythagorean identity. So now I can say this right here is sine squared theta, and that did equal sine squared theta like I was trying to prove. And so I did that using that first Pythagorean identity. So you are allowed to rearrange your trig identities if you need to get things to match up. So showing this real quick, if I want to convert this into, say, just degrees, so it's not in degrees, minutes, and seconds, I would go 5, hit the second, and then the angle button on the calculator, second angle. There's my degree marking. I would go for second angle, and then there's my, and then I would do 12, but then there's no second button over there. The second button's actually found on the plus sign in green. So then I hit alpha, and then the plus button. So I now know that's the same as 5.67. So they want me to do secant 5.67. Now secant, if I looked at this one right here, secant I know is the reciprocal of cosine, or I could have did it from the identities right here. Secant I know is 1 over cosine. So then I could say this is the same as 1 over cosine of that angle. So because my calculator doesn't have a secant button, so I have to use the cosine button. So I just do 1 divided by cosine of 5.67. And now my answer is negative 1.12. Okay. So you just do the reciprocal of whichever one they ask. Now, if they had said what is cosine and then just gave it to me, I don't have to worry about reciprocals. It's just if they ask you things about secant, cotangent, cosecant. You just figure out which of those trig functions is its reciprocal, and then you do 1 divided by, and then whatever the sine, cosine, or tangent of it would have been.